So this is addressing a question about how to get the signs right in this homework problem with the circuit. So there are two laws that we use to get our differential equations: Kirchhoff's voltage law and Kirchhoff's current law. The voltage law states that the sum of the voltages around any loop, which there are two loops here, will be 0. So those voltages will be voltage differences. This is signed information. It has orientation. So when I talk about like the voltage across a circuit component like this one, that could be positive or negative depending on whether I measure the voltage from here to there or the other way around. So it's a sort of directional, it's an oriented thing when we talk about the voltage across a circuit component. When we say the sum of the voltage differences or the voltages across all the circuit components in a loop should be 0, when we say that, we're saying that this happens if you are consistent about how you measure voltage. So if you measure voltage from here to there, and then from here to there, and then add those up, that should be 0. The idea being that the voltage measured from here to here is the difference. It's like the voltage here minus the voltage here. There's not really like any absolute voltage, but you can pick a point. If you want, you can pick a point in the circuit and say, like, this is voltage 0. The absolute voltage here we will declare is 0. If you arbitrarily declare an absolute voltage somewhere in the circuit, then you can interpret, you can interpret whatever the voltage, you can interpret the voltage here to be whatever you get when you look at the difference in voltage from here to here. But you see how it's signed? Which way you measure matters. So another way to put it is, you can imagine that you have an actual multimeter, like an actual voltmeter, and you stick the probes of the voltmeter, one probe here and one probe here. That will give you a certain reading for the voltage difference across the component. If you were to flip the probes around, I guess they should be different colors. So you could put the probes like this, but if you were to flip them around and put the blue one over there and the red one over there, then your voltmeter will actually read the negative of what it read before. It's measuring a voltage difference. Okay, so first point that I hope you're getting out of this is that there's no such thing as just the voltage across a component. It's actually the voltage difference in one direction across the component. So in that homework problem, we define V to be voltage across the capacitor, right? The voltage across here. But that's not really a well-defined thing until I say in which direction you're going to measure the voltage. Is it here minus here, or is it here minus here? Well, we do say that Q, so I mean, I could choose whatever I want, right? So I could choose V to be, measured in one direction or the other, and then I just have to be consistent throughout everything else that I do when I apply Kirchhoff's voltage law and Kirchhoff's current law. But there is a point where I'm sort of forced into a certain choice in the setup of the homework problem, which is the point where I say, this is a capacitor with capacitance C, and the voltage across it is 1 over C times Q, where Q is the charge on the capacitor. Now, Q is also kind of a signed quantity, right? Like, does positive Q indicate that there are positive charges on here and negative on here, or does positive Q indicate the other way around? So Q can also be positive or negative depending on the sort of direction in which you're choosing to measure Q. So in what way does saying that V is 1 over C times Q pin down the direction of V? Well, Q prime is the current through this portion of wire in the circuit, which in the homework problem we refer to as I3. Now, currents, perhaps even more obviously than voltage differences, currents are definitely signed information. They're oriented, right? Like when I talk about the current through a segment of wire, I have to say in which direction I'm talking about the current, right? So like you could get, but by flipping the sign and making it the negative of what it was, you would be flipping the direction of the actual flow of charges. So we've got two laws that we're using, Kirchhoff's voltage law and Kirchhoff's current law, and both of them rely on the voltages, the voltage differences, but not just the magnitude of the differences, but the actual sign also. And the current law relies not just on the magnitude of the current in each loop, but the direction also. So you need to keep the positive or negative sign correct. And there is a point in the homework problem where we choose a convention. So you just have to choose a convention. What is I3 going to stand for? We do choose a convention because the diagram shows I3 with an arrow like that. So all of the sign convention that you're asking about to the student that I'm answering in this video, all of the sign conventions that you're asking about come from the fact that we just chose that the variable I3 is going to be the current pointing in this direction. We have to choose something, and this is what we chose. So if I3 is going to be the current pointing in this direction, then if I want V to be the voltage, if I want V to be 1 over CQ, where Q prime is I3 rather than being negative I3, then V will have to be the voltage difference, the following voltage difference, here minus here. So the jump in voltage from here to there. So that's what we called V. And let's see, so each piece of wire, each continuous piece of wire, so like, maybe I'll do currents in blue. We've got I3 here. Each continuous piece of wire needs its own variable for the current. So there's also a current through here, through this part. And in the homework problem, we called that one I2. And there's a current through this part. And in the homework problem, we called that one I. You see they all have arrows. So there's a direction. It doesn't matter what direction you choose. Like we totally could have flipped any of these arrows, but you have to choose one and stick to it for the sake of just defining what these are. Like when you say I2, what do you mean? You mean the current flowing this way or the current flowing this way? It's a lot like when you're doing mechanics problems or like problems with, I don't know, particles moving around in space or projectile motion or something like that. If you say, oh, well, the y coordinate or the y value of the position of this particle is increasing. Well, does that mean the particle is falling or going up? We have to say which way y is being measured. It is positive y this way or that way. It's the same idea here. You have to say which way is positive I2? Is it this way or this way? And here we've chosen a way. So you just choose something. So since we chose this for I3, and we defined V to be the voltage across the capacitor and just used this formula, we're sort of forcing V to be measured like this. Similarly, since we chose I2 to be like this, to point in this direction, And since the voltage across, so this resistor had resistance, R1. So what did we say is the voltage across this? Well, you use Ohm's law, right? And we said, oh, it's I2 R1. That's the voltage drop across this resistor. But the current points in a certain direction, right? That's with the current going this way. So whatever I2 R1 is, that's actually this voltage difference, right? The voltage difference from here minus here. Voltage here minus voltage here. That's what I2 R1 is. So 1 over CQ is this voltage difference with this arrow, and I2 R1 is this voltage difference with this arrow. So when you go to apply Kirchhoff's voltage law for this loop, you have to pay attention to the sign. So Kirchhoff's voltage law, let me use yellow for that, says that this plus this, keeping yourself going the same way around the loop, those voltage differences should be 0. So the first yellow arrow, well, that's I2R, 1. And then the second yellow arrow, that's actually negative V. So there's Kirchhoff's voltage law applied to this loop here.